Welcome to the fifth and final video for kinematics and AP Physics C mechanics. In this video, we will be discussing Unit 1.5, in which we are looking at motion in 2 and 3 dimensions. We will be covering the following topics: position and displacement vectors in multiple dimensions, velocity in multiple dimensions, acceleration in multiple dimensions. We'll also look at projectile motion, and we'll cover uniform circular motion as well. First, let's take a look at position and displacement vectors. Usually, we are going to use x to describe position in one dimension, but when we need to add the y coordinates or the z coordinates to go into the 2 and 3 dimension range, we represent it using r. So we can represent positions using vectors. The position vector shown points from the origin to the object's location at coordinates 3, 4. The vector is then given by r. Displacement is going to be the change in position, which we call delta r. This is given by the final minus initial positions, or r2 minus r1, which is then x2 minus x1, y2 minus y1. For example, if an object moves from position 1 to position 2, which is 4, 5, the displacement vector is then 3, 3, as shown. Now, let's explore velocity in multiple dimensions. Velocity is the rate of change in position with respect to time. But now the velocity has components in each direction. The average velocity is the displacement delta r divided by the time interval. Instantaneous velocity is then given by the limit of the average velocity as the time interval approaches zero, which is simply the derivative of r with respect to time, or dr dt. In component form, velocity can be written as v equals vx I hat plus vy j hat plus vg j hat, where k hat, where vx and vy are the red and green arrows shown respectively for the velocity vector that has been drawn. Next, we will look at acceleration in multiple dimensions. Now, acceleration is the rate of change of velocity with respect to time. The average acceleration is then given by the change in velocity divided by the time interval. Instantaneous velocity is the limit of the average acceleration as the time interval approaches zero, which is the derivative of v with respect to t, i.e. dv dt, or the second derivative of r with respect to t, which is d squared r over dt squared. In component form, acceleration can also be written as a equals ax I hat plus vy j hat plus az k hat, where the red arrows shown represent the ay component and the green arrows represent the ax component. Now, we can apply these concepts to projectile motion, which is the motion of an object that is in the air and subject only to the acceleration due to gravity. The most important insight here is that the horizontal and vertical components of motion are independent of each other. In the horizontal direction, there is no acceleration, so the velocity remains constant. Thus, we can use x equals x naught plus v naught t to solve anything in that direction. In the vertical direction, there is a constant acceleration due to gravity, negative g. That means we can apply Vy equals V naught y minus GT and y equals y naught plus V naught yt plus 1/2 at squared, which is minus 1/2 GT squared. So if a ball is launched from a height of 1.5 meters at 30 degrees above the horizontal with a velocity of 10 meters per second, it should be possible with this understanding to determine the landing point. Finally, let's discuss uniform circular motion, which is the motion of an object in a circle with constant speed but changing velocity. Though the speed is constant, we know the velocity changes continuously because the direction of motion is changing. The velocity vector is always tangent to the circle. Since the velocity is changing, there must be an acceleration. This is a centripetal acceleration because it always points towards the center of the circle. Its magnitude is going to be v squared over r, or omega squared r, which is omega is the angular velocity. The centripetal force, by Newton's second law, is then given by mv squared over r, or m omega squared r. As an example, a car moving at 20 meters per second around a circular track with a radius of 100 meters has a centripetal acceleration given by 20 squared over 100, or 4 meters per second squared. To summarize what we have learned about motion in 2 and 3 dimensions, vectors are used to represent displacement, velocity, position, and acceleration. In projectile motion, horizontal and vertical components are independent, which means horizontal velocity and constant acceleration due to gravity vertically can be applied. In uniform circular motion, speed is constant, but velocity is continuously changing direction, resulting in centripetal acceleration. Thank you for watching, and we will see you next time.